Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are attempting what feels like a small miracle. We're trying to give you a high-speed shortcut through, well, pretty much the entire field of modern mechanical and systems engineering. We've synthesized a massive collection of material covering everything from, the high-level methodologies down to the really hands-on thermodynamic models.
It really is the ultimate convergence deep dive. Our mission here is to show you how those big strategic decisions, what we call systems thinking, is totally tied to the most detailed, granular technical processes happening on the shop floor.
Things like calculating fluid resistance or optimizing a heat exchanger.
Exactly.
We often think of them as two separate worlds, don't we? The big picture strategy over here and the detailed technical stuff over there.
But they're not. They're completely fused. You just can't have brilliant execution without a sound strategy.
And that strategy has to be grounded in the hard physics of what's actually possible to build.
Right. So we've structured this deep dive into three major areas to really highlight that connection. First, we're going to tackle the messy part, the human element, how cognitive bias messes with complex systems analysis.
Okay.
Second, we pivot to the really practical tools for efficiency, specifically design for manufacturing and assembly and classification codes. And finally, we ground ourselves in the fundamental physics you need to model dynamic systems. We're talking fluids, heat, and energy optimization.
All right, let's unpack that. Starting at the top, right, with the big picture. Systems engineering methodology. When a designer gets a challenge, the first step isn't sketching. It's something called issue formulation.
That is king. Absolutely everything starts there. The way you define a problem, the client objectives, the context, all the possible alternative, that critically influences the final outcome. It's an iterative, interactive process. Because look, if you define the wrong problem from the start,
you're guaranteed to get the wrong solution.
Yeah.
Doesn't matter how brilliant your final machine is.
Exactly. And when you're tackling these big, messy problems, the analytical methods usually fall into two big buckets. The first is what we call expert opinion methods.
Okay, so that's when you don't have hard data.
Precisely. It's essential when you don't have an established theory or reliable data. Think of, large-scale surveys or a Delphi method where you build consensus among professionals. They're useful, but, and this is a huge but, they introduce the unavoidable risk of human judgment.
Which means cognitive bias and something called value incoherence.
Yes. That's a great way to put it. People, even with the best intentions, can be really inconsistent or even contradict themselves, especially if they're already invested in a certain outcome.
I can see that. So what are the big biases we should be watching out for?
Well, one that comes up constantly is selective perception. This often leads to this desire for like a self-fulfilling prophecy where a decision maker only looks for information that supports the conclusion they already want to reach.
Right. They just filter out all the contradictory evidence. It's the classic confirmation bias loop. If you believe your new material is the best, you only run the tests that you know it will pass.
Absolutely. Then there's another one called ease of recall. If a piece of data is easy to remember, maybe it was a dramatic failure or a recent success, we subconsciously give it much more weight than data that's, buried in some report from 5 years ago.
So that completely distorts your sense of risk and probability.
Completely. And the last one is expectations. This is where we just automatically attach more validity to information that confirms what we already believe. It makes it dangerously easy to ignore the one piece of data that could have saved you from a huge, costly mistake.
So the whole point of systems engineering isn't just managing data. It's about managing our own flawed thinking.
That's it. The goal is to build a system for information acquisition and processing that improves our judgment and our choices.
But we should probably say, mental shortcuts exist for a reason, right? We can't perfectly analyze every single tiny decision.
Oh, of course not. Cognitive heuristics like satisficing are necessary.
Satisficing. That's looking for a good enough solution, not the perfect one.
Exactly. If you're just picking a standard bolt from a catalog, satisficing is perfectly rational. You don't have time to optimize that.
But if satisficing is okay for a fastener, it's absolutely fatal when you're designing a complex industrial system. And that brings us to part two, engineering efficiency, where we build disciplined systems to force that optimal outcome. Let's talk DFM&A, design for manufacturing and assembly.
DFM&A is where the rubber really meets the road on cost and quality. It breaks down into two main parts. You have DFA, design for assembly, which is all about the labor side, reducing the time and complexity of actually putting the thing together.
And then DFM, Design for manufacturing, which focuses on the material and tooling costs, making sure the part is cheap to make before you cut any steel.
A key insight from all the sources is that the single biggest win from a good DFM&A process is just a radical reduction in part count.
That's the cascade effect, isn't it?
It is.
You reduce the part count, and that automatically simplifies assembly. It lowers your overhead, it cuts assembly time, and it increases quality because there are just fewer opportunities for things to go wrong.
We have a brilliant, really tangible example of this. It's a motor drive redesign. The original assembly was pretty complex. It had 19 separate parts.
19. Okay.
After they went through the DFM&A process, they slashed that down to just 7 parts.
Wow. From 19 to 7. That's a huge reduction in complexity.
And look at the gains that came with it. This is where it hits the bottom line. Assembly time fell from 213.4 seconds down to just 86.34 seconds.
Incredible.
And even more important, the total unit manufacturing costs, the UMC went from 47.22 to 30.21.
That's a reduction of almost 17 per unit. I mean, at scale, that's millions of dollars in savings.
And that only happens when you get people out of their silos, which brings up the power of multidisciplinary teams.
Right. You need engineering, manufacturing, purchasing, marketing, even field service, all in the same room.
Because that's how you get a complete picture of the problem. What is field service actually seeing fail in the real world? What are customers telling marketing about the price? When everyone helps build the solution, everyone is committed to it.
So to manage all this complexity, even in these leaner designs, engineers need organizing tools. This is where classification and coding systems come in.
These are basically productivity tools. They reduce unnecessary variety and help with standardization. You see 2 main types. The first is monocode. Think of it like a library's Dewey Decimal System. It's hierarchical. You go from general to specific.
Yeah, there's polycode.
Polycode is more like using tags on a website. It's feature-based. A specific digit means a specific feature, so an engineer could instantly find all parts made of aluminum that also have a 5mm hole.
So you can just combine the tags you need.
Exactly. And the power of these systems is just staggering. An 8-digit alphanumeric code, for example, covering shape, size, material, that can represent 2.5 times 10 to the 7th unique combinations.
2.5 million combinations from one code.
Oh, 25 million.
25 million, wow.
That's how you manage that level of variety.
And this code then drives things downstream, like process planning. A CAPP system, a computer-aided process planning system, can use that code to instantly pull up the right manufacturing steps.
Which means the planners have to deeply understand the capabilities of all the different fabrication processes, machining, casting, forming, to choose the best one for that part. The code literally directs the production path.
Okay, so we've gone from strategic thinking to design efficiency. Now let's make the final jump into the core physics. Part 3, decoding dynamic systems. This is all about the mathematical models that underpin everything we design.
Right, because a modern engineer deals with systems that are part mechanical, part electrical, part fluid, all at once. So you need a unified way to model them. These mathematical models are usually differential equations based on physical laws.
And the key to unifying them is this idea of idealized system elements.
That's the Rosetta Stone, yes. Every system can be broken down into elements that either store energy, like a spring, dissipate energy, like a damper, or transform energy, like a motor.
And that concept works for mechanical, electrical, fluid, thermal. All of them.
It applies universally. It gives you a consistent way to model a really complex reality.
So let's get specific with fluid mechanics. We have to distinguish between real fluids and ideal fluids.
Yes. Real fluids are viscous. They deform under stress, the actual water in a pipe. Ideal fluids are non-viscous. They don't really exist, but they're incredibly useful for simplifying the first round of calculations.
And Bernoulli's equation is foundational for that.
It is. It's this beautiful, elegant statement that the sum of velocity, pressure, and potential energy is constant along a streamline. It's all about conservation of energy.
But things get weird and really counterintuitive when you add compressibility and high speeds.
This is where the physics gets fun. So in normal, slow, incompressible flow, if you make a pipe wider, the fluid slows down. We all know that.
Right.
However, in supersonic flow, Mach number greater than 1, if you have an expanding area, it actually leads to an increasing velocity.
Wait, hold on. That's completely backward. Why does the physics flip when you break the sound barrier?
Because the flow is moving faster than the pressure waves can travel upstream to signal that there's a change happening. The flow can't feel the expansion coming. So instead of slowing down, the expanding area just provides the space for the flow to accelerate. It's critical for designing things like rocket nozzles.
That is fascinating. Okay, let's shift to energy systems, thermodynamics, and the first law.
The first law is the conservation of energy law. You can't create or destroy energy, you can only change its form. But for optimization, just conserving the amount of energy isn't enough. We have to look at the quality of the energy, its usefulness, and that's where exergy comes in.
So exergy is the maximum useful work you can get out of a system.
Correct, and that idea pairs with a method called entropy generation minimization, or EGM. The whole goal of EGM is to minimize the destruction of power, that is, the irreversible loss of energy's usefulness, while a device is doing its job. It's critical for optimizing cooling systems, heat exchangers, cryogenics.
Speaking of heat exchangers, let's finish with that. Why is designing something like a big shell and tube heat exchanger so complex that it always needs computer modeling?
Because the calculations are highly iterative. You're solving these complex equations that depend on their own answers, so you have to run through these convergence loops over and over. You just can't do it by hand.
And the quality of the answer depends on the quality of your input data.
Critically, especially your temperature profiles. In the real world with complex fluids, they are not simple straight lines like in a textbook.
And on top of all that math, there are hard physical limits you can't ignore. For example, the restriction on PV squared.
Ah, yes. The product of velocity squared times density. That limit represents this constant battle between fluid dynamics and just mechanical destruction.
You want the fluid to move faster for better heat transfer.
But the mechanical physics of erosion and tube vibration fights back. That PV squared limit, it's usually kept below 4,000 pounds mass per foot second squared. That's the practical line in the sand. Go past it, and the fluid starts physically destroying the equipment. It often limits your liquid velocity to only 7 to 10 feet per second.
It's the perfect example of how the theoretical optimum gets slammed by mechanical reality.
So if you pull all this together, we started with mitigating our own cognitive biases in that first issue formulation phase. Then we moved to streamlining production with DFM&A, slashing a part count from 19 down to 7, and using coding systems that can define 25 million unique combinations. And we ended by applying fundamental physics to optimize flow and heat transfer, all while respecting hard constraints like that PV squared limit.
So being a great engineer means understanding the methodology of design just as much as you understand the math of the physics. The process is what guarantees the quality.
And this brings us right back to part 1, and it raises a really important question for you, the designer. Since we know cognitive biases like selective perception are just part of being human, and since systems like DFM&A rely on humans to set the targets and interpret the codes, how can we design processes that actively prevent that human tendency to just prove what we already believe?
How do you design a system that's so robust? It forces the selection of a truly optimal solution, even if that solution is counterintuitive or inconvenient for the team. A system that prevents us from just settling for the comfortable, good enough solution for satisficing. That question really defines the next frontier of resilient systems design.